All right, let's talk about something we all use but probably never really think about. I'm talking about the hidden world of vertical transportation. These are the powerful, totally invisible systems that make our modern cities even possible. Seriously, they're the mechanical workhorses moving millions of us every single day, and we barely give them a second thought. So let me just throw this question at you. How in the world do you move 50,000 people up 80 floors every single day? Now, this isn't some kind of riddle, right? This is a real daily logistical nightmare that skyscrapers all over the world have to solve. It's this incredible mix of engineering, physics, and even human psychology, all happening inside the walls of just one building. So, how do they pull it off? Well, the answer really starts with a fundamental problem that honestly we've created for ourselves. It's this thing we can call the vertical challenge. Think about it. Our buildings are just getting taller and taller, but our ability to climb stairs? Yeah, that's not changing. The simple truth is, for any building that's more than just a few stories high, getting people up and down mechanically isn't a luxury. It's an absolute necessity. It is the core technology that makes a high-rise, well, work. Okay, so let's meet the main players, the primary solutions to this whole vertical challenge. You could almost call them the unsung heroes of architecture and city life. And first up, of course, is the elevator. You know, it's a machine so common we barely even see it anymore, but it is a true marvel of engineering. At its heart, it's pretty simple, a platform in a shaft designed to move us from one floor to another without breaking a sweat. But, and this is a big but, as we're about to find out, not all elevators are created equal. Yeah, in the elevator world, there are really two dominant designs that do most of the heavy lifting. And what's fascinating is they work on completely different principles. You've got the traction lift and you've got the hydraulic lift. So let's do it. Let's put these two systems head to head. Because when you compare them directly, you really start to get why an engineer would pick one over the other for a specific job. First up, the traction lift. Okay, this is the undisputed champion of the skyscraper. The way to think about it is like a giant, super sophisticated pulley. On one side, you have the elevator car, the box you stand in, and on the other, there's this massive counterweight. They're both hanging on these super strong steel cables that go up and over a wheel at the top. Now, here's the genius part. Because the counterweight is balancing the car's load, the motor doesn't have to work nearly as hard. It makes the whole system incredibly efficient and really, really fast. It's the perfect design for climbing hundreds of meters into the sky. And then you have its rival, the hydraulic lift. Now this one's totally different. Instead of pulling the car up from above, this system pushes it up from below. The best analogy is a giant, really powerful syringe. You've got a pump that forces fluid, usually oil, into a cylinder. That fluid pushes a big piston up, and the elevator car is sitting right on top of it. This system is famous for being incredibly smooth and precise, but as you might guess, it's got some limitations. Okay, so when you put them side by side, you see the whole picture. They're really designed for completely different jobs, and the trade-offs are super clear. Your traction elevator, with its cables and counterweight, can go to basically unlimited heights at incredible speeds. It's really the only choice for a skyscraper. But the hydraulic elevator, with its piston and fluid, it's limited. It can't go up to about 21 meters, maybe 6 stories or so. But that super smooth ride makes it absolutely perfect for places like hospitals or low-rise apartment buildings where that comfort and precision really, really matter. All right, so all this talk about cables and high-speed lifts, it naturally leads to the question, the one I'm sure is already on your mind. It's that classic, terrifying movie scene. Yeah, what happens if the cables snap? It's got to be the #1 fear people have about elevators. So let's just tackle it head on. What really happens if that worst-case scenario actually plays out? Well, the answer, thankfully, begins with something called massive redundancy. First off, the word cable is kind of misleading. We're talking about incredibly strong woven steel ropes. And get this, just one of these ropes is strong enough to support the entire weight of the elevator car and its counterweight. But here's the thing, they don't use just one. Modern elevators use anywhere from 4 to 12 of them. So the chance of all of them snapping at the same time is, well, it's practically zero. But okay, let's play devil's advocate. Let's say the impossible does happen. The engineers have planned for that too. The moment the car starts to move too fast, a device called a speed governor kicks in. Think of it as a watchdog. It immediately trips the safety system, and that system engages a set of incredibly powerful brakes that literally clamp down onto the steel guide rails in the shaft, grinding the car to a halt. And just in case, if all of that somehow magically failed, there's one last line of defense. A huge, heavy-duty shock absorber waiting at the very bottom of the shaft, just to cushion any final impact. It's safety on top of safety. So, we've got these incredibly safe, reliable machines. That's great. But having the right hardware, that's only half the battle. The other half is this fascinating, invisible science of planning out the entire system for a building. It's called traffic analysis. Long before anyone even breaks ground, architects and engineers basically become sociologists. They use complex software to predict how everyone in the building is going to move around all day. They model the morning rush hour, the lunchtime chaos, everything. And they're trying to optimize for things like your average wait time. Their goal is to figure out the perfect formula. How many elevators do we need? How big should they be? And how fast do they have to go to keep everyone happy and moving? And this planning, it's not just on paper. It translates directly into the bones of the building itself. You see, deciding you need to move, say, 8 people at a time instead of just 4, that doesn't just mean you order a bigger elevator car. It means you have to design a bigger, stronger shaft right from the very beginning. Every single decision about how people will flow through the building has a real physical impact on its structure. But of course, elevators aren't the only players in this game, right? For moving huge crowds over short distances, there's another machine that's absolutely essential: the moving staircase itself, the escalator. I love this analogy. If elevators are like taxis, picking up small groups and taking them to specific floors, then escalators are like a constantly flowing river. They are workhorses designed for one thing and one thing only: to move a massive volume of people over a short vertical hop, between floors in a mall or down into a subway. And they do it without ever stopping. And their people-moving power is just staggering. A super simple design choice, like how wide the step is, has this massive impact on capacity. Look at this. A standard 0.6 meter step can move 5,000 people an hour. That's already a lot. But if you just increase that width to 1.2 meters, you've literally double the capacity to a whopping 10,000 people per hour. And hey, here's a cool little fact for you. Next time you're on an escalator, just kind of take a look at the angle. Almost every single escalator in the world is installed at a standard angle of exactly 30 degrees. It turns out that's the perfect sweet spot. The ideal balance between feeling comfortable, being safe, and not taking up too much space in the building. So there you have it. From the lightning-fast elevators in our tallest skyscrapers to the steady, constant flow of escalators in a busy subway station, our cities are literally built on these incredible invisible systems of movement. They're the hidden engines that make vertical living possible. So maybe the next time you step into an elevator or hop on an escalator, you'll see it a little differently. Not just as a machine, but as a crucial piece in the giant, complex puzzle that is a modern city. Which just leaves one question. What invisible system are you going to notice next?